Hello everyone and welcome back to the Calculus 1 video lecture series. Today we are going to be covering some basic derivative rules and the concept of higher order derivatives. So derivative rules are basically shortcuts to bypass the limit definition of the derivative. Because using it is so cumbersome, there are shortcuts or rules that we can use to find the derivative of any function. And what rule you use really depends on what the function looks like. And we're going to be spending pretty much the rest of this chapter covering all of the derivative rules, which are rules that you will use to take the derivative of any type of function that you could possibly run across. For example, constants. Because the slope of a horizontal line is 0 and constants are unchanging, the derivative of any constant is 0. So what we're going to be doing is we're going to be finding the derivative of all of these. So the derivative of 3 is equal to 0. The derivative of negative 10, it's a constant, its derivative is 0. And the derivative of any constant, I don't care what it is 0. So the derivative of 1,000 is 0. Now, constant multiples are a little bit different. Constant multiples involve a function that is being multiplied by some constant. And there are going to be some derivative rules that have their equivalents in limits. Because a derivative is a special type of limit, there are a few rules that derivatives have in common with limits. Constant multiples is one of them. So if you have a constant being multiplied by a function, then its derivative is just going to be that constant k times the derivative of the function. Now, the other derivative rule that we're going to cover today is called the power rule. And the power rule is the one that you're going to use most often because it is the simplest one. Now, power rule works for any numeric power. So do not try to use this when you have a variable in your exponent. Anytime that your exponent is just a number, you can use the power rule. So the power rule goes like this. If you're taking the derivative of some x to some power n, it is going to be n times x to the power of n minus 1. Summed up, the power rule says that you are going to move down the power and decrease the power by 1. So that's the power rule, and this will work for any numeric power. All you do is move down the power, and when you move down the power, it becomes a constant multiple. And then you are going to decrease the power by 1, and decreasing the power by 1 means subtracting 1. So if we're going to take the derivative of, let's say, x squared, we already found this derivative using the limit definition. So let's use the power rule. So I'm going to move down the power, so I'm going to take this exponent, move it down, and decrease the power by 1. 2 minus 1 is x to the power 1. So we get a derivative of 2x, which is what we got using the limit definition. Then if we're going to take the derivative of x to the third, because this 3 is a numeric power, we can use the power rule. So I'm going to move down the power, and then I'm going to decrease the power by 1. 3 minus 1 is x to the power 2. So the derivative of x cubed is 3x squared. Then if we're going to take the derivative of 3x to the fourth, now this is going to involve a couple of different rules. This 3 is a constant multiple, and according to the constant multiple rule, nothing special happens with them, they just kind of get carried along. So I'm just going to leave this 3 where it is, and then I'm going to focus on using the power rule to take the derivative of x to the fourth. So since this 4 is a numeric power, I'm going to move down the power, and then I'm going to decrease the power by 1, gives us x to the third. Then 3 times 4 is 12, x to the third, and then that is going to be your derivative. Now, another rule that derivatives have in common with regular limits is sums and differences. So if you have a sum, if you're taking the derivative of a sum or difference, all you have to do is just take the derivative one term at a time and add or subtract them. So when you are taking the derivative of an expression that involves more than one term, you're just going to take the derivative one term at a time. So if we're taking the derivative of this first function, I'm going to just go term by term, and I'm going to use the power rule together with the constant multiple rule. So for this 3 is a constant multiple, so I'm just going to leave it alone. Then I'm going to use the power rule for the x to the 5th. So I'm going to move down the power and decrease the power by 1. Gives me x to the 4th. Then minus, and I'm going to do the same thing to the next term. So I'm going to leave that constant multiple of 2 alone. Then I'm going to use the power rule to take the derivative of x to the 4th. So I'm going to move down the power and decrease the power by 1, x to the 3rd. Then I'm going to add to it. I'm going to leave that constant multiple of 3 where it is. And then I'm going to use power rule to take the derivative of x to the 3rd. So I will move down the power, so times 3, and then decrease the power by 1, x squared. Sorry, I'm running out of room. Then I'm going to do the same thing to the next term. So I'm going to leave that minus 7 where it is. And then remember, there is a power of 1 here. So if you were taking the derivative of x to the power 1, it is still a numeric power, so we're still going to use the power rule. So I'm going to move down the power and decrease the power by 1 gives us x to the 0. Then I'm going to take the derivative of 4. The derivative of a constant is 0. And then, yes, I'm going to clean this up a little bit. So 3 times 5 is 15, x to the 4th. And then minus 2 times 4 is 8, x to the 3rd. Plus 3 times 3 is 9, x squared. And then this negative 7 times 1 times x to the power 0. Anything to the power 0 is 1, so that derivative just becomes minus 7, and then we do not need the plus 0. So this is going to be our derivative. So then for this next one, if we are taking the derivative, because all of these powers are numbers, I am going to be using the power rule to take its derivative. So I'm going to leave the constant multiple of negative 6 where it is, and I'm going to use the power rule to take the derivative of x to the 7th. So I'm going to move down the power and then decrease the power by 1. 7 minus 1 is 6. Then minus, I'm going to leave the 12 where it is. I'm going to use the power rule on x to the power 1 here. I'm going to move down the power, and then I'm going to decrease the power by 1. 1 minus 1 is 0. Then I'm going to take the derivative of the constant. Derivative of a constant is 0. So then cleaning this up, I've got negative 42, x to the 6th, minus 12. And that is going to be our final answer, our final derivative. Now remember, power rule works on any numeric power. Anytime that your power is a number, you can use the power rule. So anytime that you can turn an expression into x to some numeric power, you are going to try and do so. This way you can use power rule. So for the square root of x, for example, if you want to turn the square root of x into an exponent, it is x to the power of 1/2. So I'm just going to rewrite this as x to the power of 1/2, and then I'm going to take its derivative. So the derivative of x to the power of 1/2, because this power is a number, I'm going to use the power rule. So I'm going to move down the power and decrease the power by 1. So 1/2 minus 1 is x to the power of negative 1/2. And to be honest, this is good enough. You do not have to rationalize this. I'm fine with this. If you want to, this is also very commonly written as 1 over 2 square root of x. You can write it that way if you want as well. And then for this next one, for the cube root of z, so again, we're going to try and write this as a variable to a numeric power. Cube root can be rewritten as z to the power of 1/3. So if we're taking the derivative, so d dz, of z to the power of 1/3, because that power is a number, I'm going to use the power rule. So I'm going to move down the power and then decrease the power by 1. Do not give me a decimal in an exponent. If your exponent is a fraction, it needs to remain a fraction. So 1/3 minus 1 is going to be negative 2/3, and to be honest, that is good enough. And then for this last one, for the 4th root of w, again, I'm going to try and write this 4th root as an exponent, which is an exponent of 1/4. So if we are taking its derivative, so the derivative with respect to w of w to the power of 1/4, I am going to use the power rule since this is a numeric power. So I'm going to move down the power, and then I'm going to decrease the power by 1. 1/4 minus 1 is negative 3/4. And then that is a good enough final answer. So power rule is really easy, and we're going to try and use it as often as possible. So I will tell you right now that the way that each of these functions are written would require something called the quotient rule, which is going to be covered in another video. Quotient rule is not very fun to use, and it is pretty complicated, and it takes a long time. So for very simple quotients like this, if you can rewrite them so that it is no longer a quotient, you're going to be better off. So I'm going to try and rewrite each of these as x to some numeric power, and then I'm going to use the power rule. So for 2 over x cubed, I'm going to do a little bit of rewriting first. And the way I'm going to rewrite this is I am going to undo all of the simplifying that I know that you were taught whenever you learned exponents. I'm going to write that x cubed in the denominator as x to the power of negative 3. You guys, I know it was drilled into your head that you should not have negative exponents and that negative exponents should always be moved into the denominator to become positive. I'm going to undo that because now that I have x to a numeric power and not a quotient, I do not have to use quotient rule. So now that it's just x to a numeric power, I can now use power rule to take its derivative, and power rule is a lot simpler and faster. So for its derivative, I'm going to use Newton's notation, f prime of x. I'm going to leave this constant multiple where it is. Then I'm going to use power rule to take the derivative of x to the power of negative 3. So I'm going to move down the power. And be very careful with this. When you decrease the power by 1, you subtract 1. So negative 3 minus 1 is actually negative 4. So then we get a derivative of negative 6, x to the power of negative 4. So then I'm going to do the same thing for this next one. I'm going to take this 1 over x to the power 1, and I am going to rewrite it so that it is no longer a quotient so that I do not have to use quotient rule. So to rewrite this so that it is no longer a quotient, I'm going to rewrite this as x to the power of negative 1. So now that I have x to a numeric power, I am now going to use power rule to find its derivative. So g prime of x, I'm going to move down the power. And then I'm going to decrease the power by 1. Negative 1 minus 1 is x to the power of negative 2. So then we are going to get a derivative of negative x to the power of negative 2. And then for this last one, I'm going to do two things. I'm going to take that negative and I am going to move it into the numerator to join the 4. And I'm going to take that x squared in a denominator, and I am going to turn it into an x to the power of negative 2 so that I no longer have to use quotient rule. I can now use power rule to take its derivative. So its derivative, h prime of x, I'm going to leave the constant multiple negative 4 where it is. And then I am going to move down the power and decrease the power by 1. Negative 2 minus 1 is x to the power of negative 3. So that gives me an h prime of x as negative 4 times negative 2 is 8. X to the power of negative 3. So you're going to try and use the power rule as much as you possibly can. So for this next one, let's test our Leibniz's notation. So we're going to calculate dg dt. Remember, that is the derivative of the function called g with respect to the variable t. This vertical bar here means evaluated at t equals 1. So what I'm going to do is I'm going to first find the derivative function dg dt, and then I am going to use it and to evaluate it at t equals 1. So I'm going to find the derivative function first, and then I'm going to plug a 1 into every single spot I see a t in the derivative. So before we go finding derivatives, I'm going to take this g of t here, and I am going to rewrite that square root as an exponent so that I can use power rule to take its derivative. So that'll give me t to the negative third plus 2 times t to the power of 1/2 minus t to the power of negative 4/5. So now that I've got it rewritten in a way that I can work with, I am now going to find its derivative. So derivative dg dt. I'm going to go term by term, and I'm going to use power rule to take its derivative. So starting with t to the negative 3, I'm going to move down the power and decrease the power by 1. Negative 3 minus 1 is t to the power of negative 4. Then I'm going to leave this 2 where it is, and then I'm going to use the power rule to take the derivative of t to the 1/2. So I'm going to move down the power and decrease the power by 1. 1/2 minus 1 is negative 1/2. Then minus, I'm going to move on to the next term. I'm going to use the power rule to take the derivative of t to the power of negative 4/5. So I'm going to move down the power, negative 4/5. And then I'm going to decrease the power by 1. Negative 4 over 5 minus 5 over 5 is negative 9 over 5. And then I'm just going to tidy this up a little bit, at least the constant, so that plugging in 1 will be a little bit easier. So I've got negative 3 times t to the power of negative 4. 2 times 1/2 is 1, so that'll be plus t to the power of negative 1/2. And then negative times negative is a positive 4/5 times t to the power of negative 9/5. So then I am now going to take dg dt, and I'm going to evaluate it when t equals 1 by taking 1 and plugging it into the derivative function into every single spot I see a t. When you plug 1 into the derivative function, what you are finding is the slope of the tangent line of your function g of x at the point t equals 1. So when we evaluate this, we are going to get approximately negative 1.2. And so that is the slope of the tangent line of g of t at t equals 1. Now for this next one, the proof for this does take a little while, and I don't want this video to get too overruly, especially because I'm actually having technical problems. You can see by the subtitles, I'm having technical issues. So we're going to try and make this as quick as possible. So the derivatives of exponential functions, we are going to revisit exponential functions later. So specifically, the derivative of e to the x is itself. The proof of this is in your book. I do encourage you to go take a look at that, since you do have to read this textbook section anyway. But the derivative of e to the x is itself. Now, this does not hold true for exponentials of other bases, such as 2 to the x or 1/3 to the x. You're going to see why later when we cover those, but the derivative of specifically e to the x is itself. Now remember, the whole point of finding derivative functions is so that you can find the slope of a tangent line. So finding the slope of the tangent line is the same as finding the numeric derivative of the function at that point. That numeric derivative that we calculated a couple slides ago was the slope of the tangent line at the point in question. So using derivative rules, we can then find the derivative function, and then we can use the derivative function to plug in the point of question and get the slope of the tangent line. Now remember, if you ever are asked to find the equation of the tangent line, you not only need the slope of the tangent line, but you also need the full coordinates of the point of tangency. Because in order to find the equation of a line, you need a point and a slope. Now, horizontal tangents. Horizontal lines have a slope of 0. So if a tangent line is horizontal, that means the derivative at that point is equal to 0. So if you were ever asked to find where does this function have a horizontal tangent, what you are asked is where is the derivative equal to 0? So let's take this function here. We have 2x minus e to the x over 2. We're going to find the equation of the tangent line at the point 0, negative 1/2. And then we are going to find the points on the graph of f for which the tangent line is horizontal. So first, finding the equation of the tangent line. Anytime that you were asked anything to do with tangent lines, you need to find the derivative. Now I'm going to do a little bit of rewriting here because I see this e to the x over 2, and again, quotient rule is not the most fun to use. So I'm just going to rewrite that as 1/2 e to the x, and then that will be easier to work with. So let's start with the derivative function. So the derivative function f prime of x, I'm going to go term by term and use the power rule. So the derivative of 2x is going to be 2, minus constant multiple of 1/2 stays where it is, and the derivative of e to the x is itself e to the x. So then we're supposed to find the equation of the tangent line at this point. So we have the point of tangency. The only thing that we are missing to write the equation of the line is the slope of the tangent line. Slope of the tangent line means you're going to find the derivative and evaluate the derivative at the point in question. So to find the slope of the tangent line at this point, I'm going to take the derivative and I'm going to evaluate it at 0. So I'm going to plug 0 into the derivative function. So I have 2 times 1/2 e to the 0, which gives me a slope of the tangent line of 3/2. Then I'm going to put this all together into the equation of the tangent line. So I can go ahead and use point slope form. So y minus the y coordinate of the point of tangency, 1/2, equals the slope of the tangent line, 3/2, times x minus the x coordinate of the point of tangency, 0. So you can leave this as y plus 1/2 equals 3x, if 3/2 x, if you want to. Or you can rewrite it in slope-intercept form by just subtracting 1/2 from both sides. So that gives us y equals 3/2 x minus 1/2. So that is the equation of the line tangent to this graph at 0, -1/2. So then for the next one, we're going to find all of the points on the graph for which the tangent line is horizontal. Remember, horizontal lines have a slope of 0, so horizontal tangents have a derivative that is equal to 0. So basically what this question is asking us to do is it is asking us to find which x-coordinates where the derivative is equal to 0. So it's just asking where is the derivative function equal to 0. So we're going to take the derivative to minus 1/2 e to the x. We're going to set it equal to 0, and we are going to solve for x. So this involves solving an exponential equation, which I know you guys have learned before. So let's just first get the exponential e to the x by itself. So I'm going to subtract 2 from both sides. Then I'm going to multiply both sides by -1/2. Sorry, I'm going to divide both sides by -1/2, or multiply both sides. I'm running out of room. -2. Sorry about that. -2 times -1/2 cancels each other out, leaving you with e to the x equals 4. Then, if you remember, in order to get a variable out of an exponent, that involves logarithms. Specifically, I'm going to use the natural log since it is the inverse of e to the x. So I'm just going to take the natural log of both sides. Natural log and e cancel each other out, leaving you with x equals the natural log of 4. So this is the x-coordinate where the tangent line is horizontal. Now, because the derivative is a function, and you now know a bunch of handy derivative rules that make finding derivative functions easy, you can actually take the derivative of the derivative function. So the derivative of the derivative is called the second derivative. So again, just like with regular derivatives, since they were developed by two different people, we have two different notations for second derivatives as well. So for Newton's notation, he just added another prime mark, so it looks something like this. And this is read as f double prime of x. Now for Leibniz's notation, it's d squared y over dx squared. Now here's where that notation comes from. He basically took the derivative function dy dx and took its derivative. And for reasons we're going to learn later, this is technically multiplication. D times d is d squared. Y over dx times dx is dx squared. I don't know why there are no parentheses. There just aren't. So we're going to go with it. So the second derivative is the derivative of the derivative function. Now, if you were to take the derivative of the second derivative, you get a third derivative. So the third derivative for Newton's notation, we add another prime mark, and this is read as f triple prime of x. And then for Leibniz's notation, we just tack on another d dx, and we get d cubed y over dx cubed. And if you take the derivative of the third derivative, you get the fourth derivative. And for Newton's notation, the prime marks kind of get out of control, so we stop using the prime marks after 3 because it just gets ridiculous after that. So this right here is not f raised to the fourth power. The reason that it's in parentheses is to differentiate it between f to the fourth power and the fourth derivative of f. So f and then that parentheses for x just means the fourth derivative of x in Newton's notation. And then in Leibniz's notation, you just tack on another d dx and you get d to the fourth y over dx to the fourth. So in general, for the nth derivative, this is going to be Newton's notation for really anything past the third derivative. It's going to be fn of x. So this just stands for the nth derivative of x in Newton's notation. The parentheses are there for a reason. It's just so that you don't get it confused with an actual exponent. This is just a higher order derivative. And then in Leibniz's notation, the nth derivative is going to be d to the ny over dx to the n. So what we're going to do, you will be responsible for each of these notations. So for the first one, we're going to calculate the third derivative of the function 3x cubed minus 5x plus 12, and we're going to use Newton's notation. So in order to get the third derivative, we do need the first two derivatives. So let's start with the first derivative, f prime of x. So I'm going to use power rule on each of these. So I'm going to leave the 3 where it is, and then I'm going to move down the power. 3 times 3 is 9, and then I'm going to decrease the power by 1, x squared. Then minus derivative of 5x is 5, and then derivative of plus 12 is 0. Now to get the second derivative, I'm going to take the derivative of the derivative. So the second derivative, f double prime of x, I'm going to go from here, and I'm going to use the power rule. So I'm going to leave the constant multiple where it is, then move down the power. 9 times 2 is 18. Decrease the power by 1, x to the power 1. And then derivative of minus 5 is 0. So 18x is the second derivative. So then for the third derivative, which is f triple prime of x, I'm going to go from the second derivative, and I'm going to use power rule to take its derivative. So derivative of 18x is 18. Now, I know I didn't ask for it here, but the fourth derivative would be 0, the fifth derivative would be 0, and so on. So for polynomials, the higher order derivatives do eventually go to 0. That is not going to happen with other functions. So taking a look at this next one, we're going to calculate the third derivative of the function y equals 3t plus 2e to the t, and this time we're going to use Leibniz's notation. So let's start with the first derivative. So the first derivative is going to be dy dt, and I'm going to use power rule. So derivative of 3t is 3, plus I'm going to leave the constant multiple of 2 where it is. Derivative of e to the t is itself e to the t. So then for the second derivative is going to be d squared y over dt squared. I'm going to go take the derivative of the first derivative. So derivative of 3 is 0. I'm going to leave the 2 where it is. Derivative of e to the t is e to the t. Then for the third derivative is going to be d cubed y over dt cubed. Derivative of 2e to the t is 2e to the t. And do you think this is ever going to stop? Probably not. The fourth derivative is going to be 2e to the t. The fifth derivative is going to be 2e to the t. So the higher order derivatives for this function actually never stop. They're just 2e to the t for 4, 5, 6, and forever and ever. So that is it for derivative rules and higher order derivatives. I'm sorry about the glitchy subtitles and the glitchy stylus. I am doing the best that I can with the technology that I have at my disposal. So thank you all very much for watching, and I will see you guys in the next video for more derivative rules. We're going to be covering product rule and quotient rule. So see you next time. Bye-bye.